All right, welcome back. Today, we're tackling something huge. We're talking about one of the most powerful and honestly, one of the most misunderstood technologies on the entire planet, the nuclear reactor. We're going to go from the deepest, tiniest secrets of the atom all the way up to those massive concrete domes that power our world.
And really, it all boils down to this one simple question. How do you even get energy from an atom? You know, for the longest time, science thought the answer was all about the electrons, those little particles just zipping around on the outside. But it turns out that was only a tiny, tiny part of the story. Because to really get a grip on the atom, physicists in the early 20th century had to get weird. They discovered that things like electrons aren't just little balls. They actually behave like waves. Think about it like a guitar string. It can only vibrate at specific frequencies to make specific notes, right? Well, an electron is kind of the same. It can only exist in these very specific orbits where its wave fits just perfectly. It's a mind-bending idea, for sure. But the real power, the game-changing energy, wasn't hiding in those electron orbits at all.
Nope. The real treasure chest was locked away somewhere else entirely. It was hidden deep, deep inside the atom's very dense core, the nucleus. And this is where our journey into the reactor truly begins.
So, Section 1, a crack in the atom. All right, so how did we even get into that nucleus in the first place? Well, it wasn't just one discovery. It was this rapid-fire sequence of breakthroughs that, and I mean this literally, changed the world forever.
And when I say fast, I mean incredibly fast. In 1932, James Chadwick finds the neutron. You can think of it as the perfect little key or maybe a subatomic bullet. Just 6 years later, you've got Otto Hahn and Fritz Strassmann firing these neutrons at uranium, and what they found, it just baffled them. They found stuff like barium, which is way, way lighter than uranium. They'd split the atom, but they had no idea how. That aha moment, the actual explanation, came from two other scientists, Lise Meitner and Otto Frisch. They're the ones who finally put a name to it, fission.
But here's where things got really interesting. This discovery came with a huge puzzle. When they added up the mass of all the little pieces that flew off, it was less than the original uranium atom. Like, mass had just vanished. Poof, gone. This wasn't some measurement error. This was the famous mass defect, and it's where Einstein's legendary equation E=mc² crashes onto the scene. That missing mass hadn't disappeared at all. It had been converted directly into a tremendous amount of energy.
Okay, Section 2, the unstoppable chain reaction. So look, getting energy from one single atom, that's cool, but it's not enough to power a city. The real secret sauce of nuclear power, the thing that makes it so potent, is creating an atomic fire that can sustain itself.
And this is how that fire works. It's called a chain reaction. Step 1. A neutron hits a uranium-235 nucleus. Boom. Step 2, the nucleus splits apart, releasing a massive burst of energy. But here's the kicker. Step 3. The split also releases 2 or 3 brand new super-fast neutrons. And what do? Step 4. They go on to hit other uranium nuclei, repeating the whole process all over again. It's this incredible cascade. One event triggers a few more, which trigger a few more. It grows exponentially. It's an atomic domino effect.
Which brings us to maybe the single most important question in the entire history of nuclear engineering. If this reaction just keeps feeding itself and growing, how on earth do you keep it from just exploding? Because let's be real, an uncontrolled chain reaction, that's a bomb. So how do you tame?
Section 3. Building the atomic furnace. The answer to that question is the nuclear reactor. It's this incredible machine, meticulously engineered to do two things at once. Keep that atomic fire going, but also keep it perfectly under control.
And honestly, this is the absolute best way to think about a reactor. Forget all the complexity for just a second. At its heart, a nuclear reactor is just an exotic heat source. Its main job is stunningly simple. Generate an insane amount of heat from that chain reaction and do it safely. Once you have that heat, you're just doing what a coal or gas plant does. You're boiling water, making steam, and using that steam to spin a turbine and generate electricity.
So how do you actually control that heat? Well, you use a gas pedal and a brake pedal, just like in a car. The gas pedal is something called a moderator, usually water or graphite. Now this is a little counterintuitive.
But the moderator actually slows the neutrons down. Turns out, slower neutrons are way more likely to be captured by other uranium atoms, which helps keep the reaction going. It's the accelerator. And the brakes? Those are the control rods. They're made of materials like boron that are basically neutron sponges. You lower them into the reactor core, they soak up the extra neutrons, and the reaction slows down. You pull them out, and it speeds back up.
And this balancing act has a special name: criticality. Now, when you hear a reactor has gone critical, it sounds bad, but it's not. It's actually exactly what you want. Critical just means the reaction is perfectly balanced and self-sustaining. It's like your car cruising at a constant speed. One fission event leads to exactly one more fission event. If it's subcritical, the reaction is dying out. Your car is slowing down. If it's supercritical, the reaction is accelerating. Your car is speeding up. And the reactor operators are constantly using those control rods to keep it right in that critical sweet spot.
So if we put it all together, you can see that pretty much every reactor is built from these same essential building blocks. You've got your fuel, usually pellets of uranium-235. You need a moderator to keep the reaction chugging along. You have your control rods to act as the brakes. You need a coolant, like water, to carry all that heat away from the core. And finally, you wrap the whole thing in a massive containment structure, a super thick shell of steel-reinforced concrete to keep everything safely sealed off from the outside world.
Section 4. Blueprints for a reactor. But here's the thing. Just because all reactors share these basic parts doesn't mean they're all built the same way. Not at all. There are actually many, many different blueprints for building an atomic furnace. And the choice of which parts you use, it makes a huge difference. Let's just look at one part, the moderator. You can see from this chart that one technology just completely dominates the landscape. A whopping 75% of all the reactors in the world use ordinary, plain vanilla, light water as their moderator. These are, unsurprisingly, called light water reactors. And they generally come in two main flavors.
Okay, so the most common design by far is the pressurized water reactor, or PWR. The key here is that it uses two separate loops of water. The first loop gets incredibly hot from the reactor core, but it's kept under such extreme pressure that the water literally can't boil. This superheated water then runs through a heat exchanger, which boils the water in a second separate loop. That steam is what spins the turbine. The big advantage here? The radioactive water from the core never ever leaves the main containment building. Now the other main type is the boiling water reactor, or BWR. It's a simpler design, it only has one loop. The water boils right inside the reactor vessel itself, and that radioactive steam goes directly to spin the turbine. It's simpler plumbing, yeah, maybe a bit cheaper, but it also means you have to be extra careful with maintenance on the turbine since it's been exposed to radioactive materials.
But here is the part that just blows my mind. These two designs we just talked about, PWRs and BWRs, they're just the tip of the iceberg. They're just two of the designs we've decided to build on a large scale. When you actually look at all the possible combinations of different fuels, moderators, and coolants, there are over 1 million potential reactor designs. 1 million! We have barely scratched the surface of what's even possible. Section 5, the future of fission. So that really brings us to the final and I think most exciting part of this whole story. Where do we go from here? What does the future of fission even look like?
I mean, with literally 1 million possible designs out there, you have to ask, are the water-cooled reactors we rely on today the end of the line? Are they the final word in fission technology? Or are they just the Model T, the very first generation?
Well, innovation is definitely not dead. Not by a long shot. Researchers are working on some pretty radical advanced designs. You've got things like sodium-cooled fast reactors, which could actually breathe their own fuel and even burn up existing nuclear waste. Then there are molten salt reactors, which use liquid fuel instead of solid rods. This means they could potentially be refueled and have waste removed continuously while still running. And then there are high-temperature gas reactors, which operate at such incredible heat they could be used for major industrial processes, like creating hydrogen fuel, going way beyond just making electricity.
And that really leaves us with this final thought. From the strange, wave-like behavior of a single tiny electron to 1 million different blueprints for an atomic machine, the story of the nuclear reactor is really a story of human ingenuity. It's about harnessing an almost unimaginable power.
But every single design, every blueprint, comes with its own unique set of promises and its own set of problems. So the real question for our future isn't just how we build a reactor. It's about which one we choose to build next.